Hello, my name is Tusi Memebo, software engineering student at Makerere University, along with my partner, Abisha Bangana, and we are going to be discussing NeoScreen, a multimodal AI for neonatal respiratory distress detection. This is going to be our roadmap as we present, starting from the background and introduction all the way to acknowledgement and references. So, what is our background? First of all, neonatal respiratory distress is the third leading cause of neonatal mortality rate across the world. And 47% of deaths under 5 years old are caused by respiratory distress. And then 98% of these occur in LMICs. So it's detectable by audio. This is by grunting, stridor, and apnea, which are described. And then vital signs like cyanosis, whereby the spatial oxygen is less than 90%, the bradycardia, where the heart rate is less than 100 beats per minute, and where respiratory rate is greater than 60 breaths per minute. So what is our problem statement? The clinical problem is that there is inconsistent diagnosis, that different medical workers predict or diagnose different diseases. So someone could say it's not distress, yet it's actually distress according to their experience and other factors. And then the shortage of experts. So people miss early signs, like the way the child is breathing, and that can lead to deaths that were preventable, because of delayed intervention. And then the statistics clearly show that this is a serious problem. So what is our computational problem? There is tabular data. We have tabular data, which is clinical variables that we've talked about, the respiratory rate, the spatial oxygen. Then there's audio data, which is the sounds, the respiratory sounds like grunting, how the child is breathing. And then there's unpaired sources, that there's no source that has both clinical and audio data, that they are separate. The clinical data is alone and the audio data is alone. And then there's an imbalance that the distress cases are only 2.6% in the data. So we're not exactly getting a lot of data about the problem we're trying to solve.
Thank you. So moving on, we are looking at the related works whereby we made some research to look at people that have made previous research in regards to respiratory distress and to see what and how they did it and how we can improve on that. So for the related works, we found that most authors actually dealt with audio-only datasets, whereby they focused on different things. As we can see, some focused on sepsis and respiratory distress from infant cries, and others on birth asphyxia detection. Others looked at the distinction between sepsis and RDS, whereas there was one also in 2024 that looked at grunting severity prediction, but all these focused on audio data only, and there was no integration with clinical variables such as harmonic pressure. Then we also looked at works which followed multimodal approaches, but here we found that even though they were doing multimodal, the limitation that they had was that they were looking at general age groups, for example, adults and children all together mixed and not neonatal specific. And and then we also had one whereby with adults, there was actually video required to be able to work with that kind of data. So here the research gap was that there was existing multimodal work, though it was generally for adults or all age groups mixed up and not neonatal specific. Then from here, the research gap that we managed to identify was that the works that exist either used audio only or used clinical data only, or did a combination of both, but then they were not specific to the population, to our target population, which is neonates. And therefore, that's where our solution comes in, whereby our population is going to be neonates, and the data, we are going to look at a multimodal approach of both clinical data and acoustic analysis.
Thank you, Abisha. So for our research questions and objectives, we are trying to find out what acoustic features can best characterize the respiratory distress, and this is through the grunting and stridor. And then does multimodal fusion outperform single modality? So using both clinical and audio data, is it going to help to improve the model, or it doesn't really matter? And then which fusion strategy is optimal for the task we're trying to perform? Late fusion, early fusion, or intermediate? So then what are our objectives? What are we trying to achieve with this project? We're trying to extract acoustic features from the data and then to develop a multimodal pipeline. And then after developing the pipeline and doing the model, we want to evaluate its performance and then deploy the prototype and test and see how well it does. So how are we going to achieve this? The steps we're going to take, we're going to pre-process the data, both the audio and the clinical data, and then extract the features that are important for this particular problem. And then we shall do fusion of both the clinical and the audio data, and then be able to classify the features that can characterize this illness in the neonates.
Thank you. So moving on from our methodology, we are also looking at how we are going to sketch our system, or what we call the system architecture. And like we said, using our multimodal approach, we are going to have tabular data, which has the clinical features like birth weight, respiratory rate, as well as our audio data, which has respiratory sounds like grunting and stridor. So with the tabular data, we pre-process it through normalization and encoding, and we get features such as features to be able to determine the clinical vector. Whereas with audio data, we are going to pre-process it through filtering, segmentation, and denoising to get audio features such as harmonic ratio and CNN embeddings. And with that, we are going to fuse the features from both types of data using early fusion and late fusion. With early fusion, we are going to look at feature concatenation. With late fusion, we look at decision level ensemble. After that, we are going to put them in a classifier using gradient boosting, specifically the XG boost. And from there, we shall look at the risk output basing off the probability score. Then for our datasets that we are using, we have a synthetic neonatal dataset, which is going to provide us with the clinical data. And here, that synthetic dataset has about 30,000 records with scenarios ranging from the low, moderate, and high burden, with key features such as the Apgar temperature, the respiratory rate, birth weight, and here the respiratory distress prevalence is actually just 2.6%. 2.6% out of all the 30,000 records that we have. Whereas with the respiratory sound datasets, or where we're going to collect from our audio data, we have different features such as we have different datasets such as SPR sound, which will provide us with respiratory recordings. And then we have the ICBHI 2017, which will provide us with labeled recordings. And here we shall have about 920 records. And we are also looking at the HLS CMDS, which will provide us with clinical and sound samples with about 535 samples.
Thank you, Abisha. So we were able to get a synthetic dataset for neonates from Hugging Face, and we carried out some exploratory data analysis, and we combined 3 sub-datasets that are moderate burden, low burden, and high burden, as you can see from this pie chart in the center, where these are specifying the conditions of the medical facilities where this data would have been gotten. So we have the primary outcome, which can be healthy, low birth weight, and the different conditions the neonates may have, respiratory distress, neonatal sepsis. So we are exploring the relationship between categorical features and the primary outcome. So we're seeing in females and males how much the gender is related to the outcome if the child has respiratory distress, to kind of get the relevance of the features. So here we see moderate, high, and low to see if the medical facilities contribute to the primary outcome. And we can see for low, there is really very few cases of respiratory distress. And then here we see delivery mode, vaginal and cesarean, and we see cesarean has very few cases of illnesses among the neonates. And then here we look at the birth weight. Is it a normal birth weight, low birth weight, extremely low birth weight, macrosomia, and then very low birth weight? So we're kind of seeing what is the relationship between the birth weight and the illnesses. And then normal birth weight kind of has very few cases of low birth weight term and respiratory distress, whereas very low birth weight at the extreme right has some numbers of preterm complications. So then we look at preterm and late preterm, which is how early or late the child was given birth to. So we see very preterm here has preterm complications, and then late preterm has moderate a bit. We also went ahead to explore the features to kind of see their distribution. So here for sex or gender, there are only 2 values, male and female, and then delivery mode as well, where most cases are vaginal and then very few are cesarean. So we're seeing gestation age in weeks, which is how long the mother has been pregnant before giving birth, which can determine if someone is preterm, if a child is preterm or not. And then we have how old the mother was, which is maternal age in years, when they gave birth, and is this relevant to the problem we're trying to solve? The head circumference of the child at birth, and then the birth weight, how heavy were they when they were born? And then here we have some vital clinical data that can be indicators of illnesses. So we have temperature, and then we have the heart rate, we have the respiratory rate, and then we have spatial oxygen, and then Apgar 1 minute and Apgar 5 minutes, which is basically if there was an emergency within 1 minute and 5 minutes of giving birth to this infant. And then we have parity, which is the child a firstborn, a secondborn, things like that. And then histogram of ID, which is kind of unique for every record. So it's not really relevant. So the problem with most of this data is that most data we have is for healthy neonates. So it's kind of hard to classify. And then here we have a relationship between the respiratory rate and the primary outcome. So healthy babies have a certain range of the respiratory rate between 70 and 30. And then people with respiratory distress can have respiratory rate up to 100 breaths per minute. So this is a key indicator. And then the gestational age versus primary outcome, which is showing if the time or how preterm the child was can determine if they're going to be sick or not. And here we see that gestational age also has a relationship with respiratory rate, that normal respiratory rate is between 30 and 70, but we see that most cases above 70 breaths per minute are those that are a bit preterm. So there's a relationship there. So here we have a correlation heat map where we're trying to find out if there is correlation between any of the features in our dataset. So we see that birth weight is highly correlating with gestational age in weeks, which means if someone is born preterm, they're most likely to be smaller or less heavy. Then we have a high correlation between Apgar 1 minute and Apgar 5 minutes, which makes sense. If someone had an emergency in the first minute, that automatically counts as having an emergency within the first 5 minutes. I'll hand over to Abisha.
Thank you. So based off our EDA, we have results that were expected and how we are analyzing them moving forward. And one is looking at the importance of the features that we have extracted and which ones matter most. So some of the features we looked at: harmonic ratio, respiratory rate, gestational age, and others. And what came up as our top predictor was harmonic ratio with an importance score of 0.21. And based off this, we managed to gather a key insight, which was that grunting, which is also expiratory breathing or a loud noise that is made as one is exhaling, is the strongest predictor of respiratory distress with harmonic ratio analysis, providing critical diagnostic information, while audio features tend to contribute about 43% of the predictive power. So moving on, we also compared performance based on tabular data only, looking at late fusion and early fusion. And our best performance for this was early fusion with an area under curve score of 0.91 with a sensitivity of 88% and a specificity of 92%. And from this, we gathered that early fusion captures cross-modal interactions. So we also managed to identify some limitations with the datasets that we are using and how to countermeasure those challenges or limitations. One is unpaired data, whereby you find that clinical data was gotten from a different synthetic data set, and the audio data is also gotten from different data sets and different units. So with this, our countermeasure is prospective collection, whereby we can go to a specific, maybe hospital or a specific institution that can provide data that is paired or correlating with each other. We have class imbalance, whereby you find that out of over the 30,000 records that were in the synthetic dataset, only about 2.6% of those were actually positive cases that were going to be useful in our problem. And for this, the countermeasure is to oversample synthetic data and to weight the classes. Then we also have a challenge of age mismatch, whereby the audio datasets were spanning different age groups, even though our problem was focusing on a specific age group, which was neonates. And for this, our countermeasure is transfer learning, which is to fine-tune on neonatal specific data. Then what we are looking at moving forward, we have what we've finished, which is our literature review, looking at the taxonomy based off the major 8 layers, and also getting results on the synthetic data set. And what is in progress currently is the documentation and writing of the report. And some of the future works are getting approval or getting an ethics approval from the hospital that we tend to get from data to enable us with our prospective collection. So in conclusion, we've realized from our key insight that grunting was one of the major predictors of respiratory distress. And from there, we know that if our baseline risk is 0.78 in a neonate without grunting, that means that risk is adjusted to be lowered by 60% to 0.31. Whereas in a neonate, if there is grunting involved, the risk actually increases by 18% to a 0.92. And these are some of our acknowledgements. We have the data providers for the publicly available datasets, our institution, Makerere University, where we are students, as well as DeepSeek AI, which assisted us with reviewing and editing of our content. Then these are some of the references that we managed to look into as we were researching related works or works that are related to our problem. And in conclusion, we want to once again say that this has been the research team made up of Abisha Bengana, which is I, and my partner member Tosime. And we also give thanks to our supervisor, Dr. Galiwango Marvin at Makerere University. And we end by saying that every grunting baby deserves a chance. Thank you. Thank you very much.